introduction. So thank you for giving me the opportunity to talk and for the invitation. So I will talk about variance reduction in random homogenization, and I apologize for the title, which is a bit too long, but let's break this down. So there's random homogenization. So I will first talk about homogenization, then random homogenization, then variance reduction in random homogenization, and finally, I will come back to the topic. Okay, so there's been actually an effort in the team into developing variance reduction technique in random homogenization these past years. So this is sort of the latest iteration, and this is joint work with Claude Bris and Legoll from the same INRIA team. Okay, so when you talk to material science people, they tend to tell you that, for instance, in airplane wings, you've got some very complicated materials which involve different scales. So, for instance, this is an airplane wing, and this is of the size of the macrometer, and this is of this, you should consider that this should be of the size of the meter, or at least if you want to know how an airplane wing bends, you must simulate it on the side of the meter. So let's think of a very easy way to model this, which is a simple linear elliptic equation in divergence form. And I will embed the fact that the material is very complex and at the side of the macrometer into the fact that A depends on the small parameter epsilon, and hence the solution depends also on the small parameter epsilon. And okay, and we've seen this equation arise in previous talks. Okay, so let's start with a modeling assumption. So let's assume that, for instance, A is just one single periodic function, which is a scale, and see where is this lead. Okay, let's start. So I consider a periodic function, and I look at my equation in the I, and what the first statement in homogenization theory is really a compactness statement, which tells me that actually this equation converges in the sense of gamma convergence or etc. Towards a limiting equation in the sense that there exists A star such that, okay? And this equation is much more simple in the sense that it no longer involves the fine scale epsilon. So this is really where homogenization is useful, you would say. And secondly, the second statement is the fact that actually you've got a formula for A star, which is linked to the fact that A has some structure, and the formula is just some average of A. So let's forget about this part for now. This is just an average of A, except for a tiny correction, which is solved using the so-called corrector equation. So this corrector equation amounts to the fact that you have to know the environment around you, and the fine environment is somehow lifted from the fine scale to the coarse scale. Okay? So this equation is at the fine scale and thus posed on RD, but thanks to the fact that we are in a periodic setting, it is actually very easy because we've got a periodic boundary condition, and then actually the equation is posed in the periodic cell. So this is very easy. So now you come back to the mechanical people, and they tell you that actually perhaps you've gone a bit overboard by assuming that A was periodic, because this is not so periodic, right? So fibers are missing here. So perhaps you've got some a network much more intertwined in some region. So I don't know. Okay, perhaps assuming it was periodic is a bit too much. So let's try to relax this hypothesis. And to relax it, we will assume that A is, okay, it's the rescaling of some function, but the function is random. So now we embed our problem into a family of equations indexed by epsilon, but the coefficient field of which is random. Okay, so it's a bit complicated, but let's say that this material corresponds to one realization of some otherwise much more general random field. Okay, so same equation, same compactness result. Okay, but now the A star, there is still a formula because I have some structure. There is still a formula which involves an expectation. Okay, so far so good. And the trouble is there is that the corrector equation is still posed in RD, but now there is no way that I can lift it back into a compact space. Okay? So this is the corrector equation, and I will spend some time on it because basically this is the problem I will address. Okay, so those guys are deterministic, and I would like to add that this PDE is posed in RD. So if D equals 1, okay, D equals 2, okay, D equals 3, okay. But bear in mind that we cannot solve PDE in dimension, for instance, 3n, where n is large. Okay, right. Okay, and I must add also something which is, okay, I will add it later. So let's solve this PDE. So I cannot solve it by hand. I have to do numerics. And to do numerics, actually, I cannot solve it on RD in the whole space. I have to truncate. So let me truncate. So I truncate this, and I add some fancy periodic boundary conditions. Okay, why not? And actually, why not? It's because if you pay attention, you see that actually WP is not supposed to decrease. So this is a problem. This is not a localized problem, if you wish. So that's why we put some periodic boundary condition. And that's why the approximation of the solution of this equation is so hard. Okay? So let me truncate. I truncate. And then I've got some guy which somehow mimics this formula, except that it's posed on some very large supercell cell. Okay? So I've got an ergodic theorem. The ergodic theorem states that almost surely that guy converges to that guy. So far, so good. But, and there is a big but here, this guy is random. Okay. So this is pretty bad because I'm actually approximating a deterministic quantity by a random quantity. So I'm doing a lot of error, and I will have to control this error. So the first thing I will do is that I will take an empirical mean of the aforementioned estimator, and I will try to control the error. Okay. So let me decompose the error. I've got this error, which is completely deterministic. Okay, the bias error, which I will not address. And okay, let me say a word later about it. And there is a purely statistic error, which is in fact dominating. So if I want to know how this error behaves, I can as well use a central limit theorem at n fixed, and as m goes to infinity. So I've got this asymptotic confidence interval. So it's fair to say that this error is controlled by the variance of A star. Okay. Divided by square root of m, of course. So let me come back to that. So actually, this statistical error is then controlled by 1 over the square root of m times the variance of A star n. And if you do numerics, or recently if you do theoretics, then you know that the variance of A star n is 1 over n to the d up to some correction factor. Okay, let's not speak about that. The important point is that it's 1 over d over 2. Okay? On the other hand, the systematic error decreases like n to the d. So it is expected, and we can see it, that the statistical error is much larger than the systematic error. Okay? So I'm not in the situation where the supercell is so large that those two errors are very small, and I'm in a situation where this error is larger on the other hand. Okay, so that is why what I will do in my talk is just the following thing. I will try to construct an alternate estimate of A star, which is alternate to that one, which has a smaller variance. Okay, and in a nutshell, what I will do is just to pick not just every realization, which might be completely crazy. For instance, I could put something which happens not so often. I will select my realization so that perhaps it has a lower variance, and then I'm in good shape. Okay, so time for an example. Well, first, time for questions. Do you have questions about that? So far, so good? Yeah?
How does M come into play there? Because your error is controlled by square root of M in the denominator.
So this is the M here. So I've got realization, and I will average each of the A star M I've built here. I will average them out, and you can see that as M grows larger, I will converge towards the expectation at the rate of the TCL, central limit theorem, and okay, so that's why the M. Other questions? Okay, so that's all. Okay, let's pick an example. So let's see what. Yeah.
What can you tweak to reduce the variance?
I will show you how to reduce the variance.
So
but
I mean, where do you have the freedom to reduce A star M because everything is fixed, no?
yeah, everything is fixed, but you see that the variance of A star M appears here because this is because I use this estimator. See, if I pick another estimator, then I will have the variance of some other guy here.
Of course, and that's right. I see.
Exactly.
Yeah.
Okay. So this is how we model the airplane wing. So I've got just a grid, and on the grid, I decide with some probability either to pick the matrix, that's a dark matrix, or some periodic coefficient field. Okay, this gives me a stationary field, and okay, and chi1 stands for the place where I have decided to put the inclusions here. Okay, and for the sake of convenience, and no, actually to push the analysis at the end, I will need to have C0, which is a constant, which corresponds here to the fact that the matrix is just a constant matrix. Okay, so I've got a coefficient field, which is a constant matrix here, and some periodic matrix here. Okay, so far so good. And when you go to mechanics people, they tell you that, oh, well, actually, you don't need to go to very large supercell limits. You can stop at some point. You can stop because when your supercell is large enough, the fluctuation, you can completely neglect them. Wow. And actually, so why would it be not so false, let's say? Well, if you've got, so they explain to you that, yeah, because at some point you've got the correct volumic proportions, you've got correct correlation functions, so say the empirical estimator of the expectation of A of x times F of y is not so bad, and some other things. So let's try to inspire ourselves from this observation into having an estimator which is a little bit better. And so now comes into play the parameter that I've not talked about. So I've got A, which depends on eta, and I will just make an asymptotic development with respect to eta in order to develop another model. Right. So let me do this expansion, and I will explain to you later why it's useful. Okay. So I've got an expansion. So let's forget about the formula here. It's just for sure, okay? And I can do an expansion of A star eta close to eta equals 0. And I've got some formula which I don't ask you to remember for now. Just remember that I've got a formula for A star, what I'm after. I've got also a formula for what I'm able to compute. I can also say that it expands as a power series in eta, and the same for the homogenized coefficient that I'm able to compute. That's the point. So why not try to make it so that they agree? Let's see if this comes back to the intuition of the mechanician people. Okay, so the basics of the algorithm is the following. So I will do a Monte Carlo mean, as I told you before, but only on configuration omega that satisfies those conditions, okay? So I will explain to you how I am able to evaluate those conditions in an efficient manner, because if I'm not able to evaluate them in the first place, okay, it's game over. So the first thing to do is to know how to evaluate them, and then to design an algorithm such that building them is not too costly. And I will come back to that later. Sorry? I will need to compute them, and I will explain to you how to compute them. Of course. Okay. So that's the sentence. Let's see the zero-order condition, because actually there's some kind of logic which helps the understanding. So I've got this equation. I put it back to you from before. This equation is for the expansion of the corrector. And it will help me constructing this guy. And actually, the solution, the periodic solution of this equation is 0 up to a constant. Okay, very good. And the solution, because C is a constant, okay? So I pick, so I know that 0 is a solution, then, okay? And actually, the stationary solution of this equation on RD, which is a limiting counterpart, is also 0 up to a constant. Okay, very well. So I've got this guy, which is actually equal to this guy. No work to do. Very good. So every realization automatically satisfies the zero-order condition, which is just a consistency condition in some sense. Okay. Let's move on to first order. Hopefully it's a little bit more interesting. So now I've got the same operator, but a different right-hand side, which amounts from the perturbation expanded at the first order, right? And so I've got, I recall the formula of the first order correction matrix. And it turns out that since this guy is periodic, then it means that, and this guy a constant, I can just smuggle this little C0 here out of the integral, and this guy cancels out. Okay? And now I've got just this. And here, for similar reasons, let's say, I've got this guy that cancels out, and I've got this, and this is 0, and I've got just a condition at the first order, which is just like this. Okay, so let's just think about it. If C1 minus C0 is the identity matrix, okay. If this guy is the identity, I can cancel it out, and it just says that the realization that is, in some sense, the best should satisfy the fact that the volumic proportion of fibers, of inclusions, should match the asymptotic one. Okay, no rocket science here. But still, we will recover something which was intuitive. And we've got an extra factor. Okay, second order condition. So I've got this equation, which was I reduce. So okay, so let me skip the technical details, and I've got another condition, and I've got here a solution which at the previous slide I didn't need even to compute. Now I've got to compute it, and luckily enough, actually this is somehow linear in chi1. So on the hierarchy of equation, now let's skip technical details. It's just the fact, what I want to point out is just the fact that this equation actually means that I've got a quadratic form in chi, and I want it to match its asymptotic limits. Okay, second command. This you could see as some kind of correlation. And this you could see as some kind of asymptotic correlation. So same remark. We recover the mechanic intuition, and we got the factor here, which are important. Okay. So let's pursue in this direction, but I will need a bit more structure on A in order to be able to compute up to the second order each and every coefficient. Okay, so now I will assume that A is some kind of constant matrix, say the identity, plus a coefficient field that I assume to be constant on each cell, okay? And the constant is random a priori, and I will assume it to be IID. And for instance, Bernoulli, and let's say it takes value -1 or +1 with equal probability. Okay, it doesn't really matter at this point. And I rewrite the first order condition as just to say that in this case, I've got an equal amount of +1 and of -1. And the second order condition just tells me that I've got something like that. Now, what I need to explain to you is how to compute the blue quantities. And when I've explained to you how to compute the blue quantities, I will be in good shape to evaluate these conditions. So, okay, just the first order condition first. Okay, so actually this is very easy to implement. So I will tell you later how the numerics work, but you can see that it's actually very easy to implement. Yep. Yeah, we will do that. Yeah. The second order condition is a little bit more difficult because I've got to compute those guys, and actually to compute those guys, I just have to flash back into the solution of this guy, and it seems a bit actually it's not too difficult because I've got here a constant matrix. I've just got to compute one single PDE because this there is some kind of superposition principle, if you wish, and I can say that chi1 is a sum of xk indicator of the corresponding cell. And so I've got one PDE to solve, I evaluate something, and I've got my coefficients, so no sweat. On the other hand, this guy is a bit more tricky to evaluate, and I've got to solve a PDE which is posed on the entire space. So I am able to solve that PDE just because its right-hand side is as compact support. So it means that actually it's a divergence of the indicator of some cell. Okay. So here it's really the linear structure that makes me able to compute those quantities. Okay. Okay. Now I can evaluate them. Does that mean I'm able to sample them? That's a different story. So actually, we are not able to sample them. And worse, actually, there need not be a omega that satisfies this relation, okay? So what we are going to do is a bit different. We are going to take the omega such that this relation is satisfied up to a small error. And I know that when n is large, that the error is small because this quantity converges to this quantity. It's just an ergodic theorem. Okay, so what I'm going to do is I'm going to select configurations such that this equality is best satisfied. So that's why we use some kind of selection method. Okay? Exactly. Exactly. Very good point. So actually, this guy I pre-compute once. Okay? So this is one PD. This is one PD. I pre-compute them once, and then I just have to evaluate this. So evaluating this need no, and that's the strength of our method, needs not to compute a corrector problem. So I select the configuration, and then on the configuration that I've selected, which I may pick 5% of them, I will solve PD. I will solve the corrector problem. So I'm not solving a corrector problem, then throwing out the answer, if you wish. I'm just solving corrector problem on configurations that I've selected beforehand. Okay, yeah? Not really. We can pick really anything. If you want, instead of doing that, for instance, we could have said, okay, let's fix a threshold, epsilon, and let's just keep realizations that are below this threshold. But if your threshold is say, for instance, fixed in with respect to n, then it's useless basically because everyone will fall into the threshold eventually. So you've got to have a threshold which depends on n, and then again, it's a bit the same as saying that you've got to pick an amount of them. So yeah, but the 5%, if picking, for instance, the 7% instead of the 5% made the approach crumble, we would be in very bad shape. So we made sure that we are not very sensitive to this 5%. This is a very good point. Okay, I will not show you the numerical test involved because it's not so interesting. The point is they exist. Okay, so let's have a look at the performance. So now you've forgotten already. So I've got a Monte Carlo estimator like this, and I made the following error decomposition. So we propose this alternate estimator. I've got also an error decomposition, but now I've committed I have committed a crime, which is this guy does not match this guy. The expectation of the conditioned set need not be equal, and it's different in general, to this expectation. So I have to pay close attention to two things. So first, I've got to reduce the variance, which is completely written in the method because we select configuration. So of course, the random space is smaller than we reduce variance. Okay, no sweat. But we've got to pay very much attention to the fact that we do not increase too much the bias. Okay, that I will detail later. Okay, so let me be completely honest with you. The variance reduction is very easy, as I told you. And the convergence, we managed to do it only in simple cases, okay? So the convergence of this guy towards A star is not so easy. But for now, let's show some satisfaction, let's say. So this is the funny part of the talk, which is the numerical results. So let's say that, for instance, in dark, I've got the Monte Carlo simulation. Okay. So I've got here the supercell size. So as n increases, I will converge to some homogeneous value. Okay, which is here. I can compute confidence interval, which is the same as I've shown you before. And the point is, I've got a convergence. It's now narrows down because I've got. But then, with our method, for instance, in red, it's the first order case. We've got much narrower confidence interval, and we really see that it converges also to the same limits. So, okay, the resolution of Monte Carlo is clearly not enough to see the limit here. Would be like, for instance, here. Okay, and in blue we've got a so narrow confidence interval that it's very great. Okay, and what about so that kind of shows that the bias is actually smaller with our method than the Monte Carlo method. This is the bias. I mean, the center of this guy as against and this I treat this guy as some kind of reference A star because the error is so small, and then I compute the center of this guy minus this guy, and I call this the bias. On a numerical perspective, it makes sense, and you can see that actually the bias is smaller with our method, and but on the other hand, we cannot know which has the smallest bias here. Okay, and what about the variance? So as I told you before, it's easy to see that the variance is reduced, and it's actually reduced by a factor, and the factor is independent of n. So let's just think about it. So why would it be that conditioning with respect to something which is true at infinity makes a difference when n is large? So actually it's not so easy to understand, but because the limit is itself deterministic, actually the variance reduction is pretty much insensitive to the supercell size. Okay? So I've got a variance reduction which is of order 10 to the minus 3 here, and 10 to the minus 5 here. So this is very interesting on the computational side. So that was the point of the remark of Max, I think, which was to say that, yeah, here. I picked the best 5% configurations. So that means that when the supercell size increases, of course, this would be closer to this. But on the other hand, I am much more picky on the configuration I choose. I expect them to be that much closer. Okay? Yes, it is. Yes, it's roughly. But I mean, you have to quantify the ergodic limits. So it's but on the so you would say it's very hard. But on the practical point of view, this is just so this converges as an ergodic limit. So you would expect this to converge at rate n to the d over 2. Just like if those guys were RID, if you wish. Okay? Does that answer the question? Okay, very good. Yeah. Maybe it's e to the 3, e to the 5. Yeah, I think so. good point. I should correct my sentence. e to the 3, e to the 5. Okay. Any other comment, questions? Okay, very good. So I told you that we can manage a simple case of convergence. So let's see how we can manage the convergence. So let's look at the 1D case. Okay, so the 1D case is actually very easy because when I look at A star n as a function of those random variables, actually this guy depends only locally on the random variables. So this is very easy to see that this guy will just meet the asymptotic value. If I condition just at the first order, I'm already at A star. So the 1D case is very easy for our approach, and we are automatically at the asymptotic limit. So you would say that this is a test on which we perform very good. But on the other hand, the 1D case is boring because we can compute everything by hands. So let's try to see what happens in a dimension which is higher. So let's assume that, for instance, A is some, I just reparameterize A as just a function here times the indicator of the cell. And I will assume X to be a Gaussian random variable. Why not? So here I embed the fact that X, that the coefficient field is IID. Okay? And so the question that I ask is the expectation of A star n under the conditioning that I've put here, does this expectation converges toward A star? So actually, this is not so easy because you would say that, okay, the law of this guy converges to some asymptotic law, and then any marginal will converge, but this is not any marginal. This guy talks to everybody, talks to x1 up to xn. So I cannot say that this depends just on x1, for instance. So I'm in pretty bad shape, and it's not so easy. So the case we were able to prove is a bit more simple. So we've put some appropriate condition on F, which is which make the problem well posed. So, for instance, F, which is isolated from 0 and bounded, and C1, and what we're able to prove is something like that. So let me spend just a few minutes to explain you why this has some relationship with what we want to prove. So I've got a mean which is equal to 0. On the other hand, it's not f of xk. So this is pretty bad. But we are able to prove that this guy goes to A star. So if, for instance, let's say that Gaussians just are, let's say that Gaussians are, well, Gaussians have tails, right? So they take negative values. Let's say that our Gaussian doesn't take negative value. Then I want to put f equals identity here, okay? And then you would have something like the homogenization of a field with a Gaussian with a Gaussian factor does converge under our conditioning. But the fact is that Gaussian takes negative value, so we cannot do that. And we've got a very weaker result. So this is a bit disappointing. Okay, I want to finish with that. So you have so I'm done. Yeah, but actually the contrast we picked in our experiment is not so low. Exactly. Okay, so the point is that what we did. Okay, so you can think of just any conditioning, right, with this approach. So as long as it's satisfied in the limit, it would make sense. But the condition you pick is in some sense the intelligence of your method. So if I pick a condition which is just so stupid, I will only get a method which is not so good. So in our case, we picked a conditioning which is, you're right, which is dependent of the fact that the contrast is somehow low. So if I've got a contrast which is, say, normal, I get something which is very good. But if I pick a very high contrast, I expect, and we saw that the method somehow gets worse and worse, which is fair. Exactly, that's what I said. Okay. Yeah. So if C naught depends on X and is a periodic matrix, because if it's not a periodic, then you're not stationary, and okay, nothing makes sense. You can do that up to the first order, and then the second order, you would have to compute this guy. And this guy is not easy to compute anymore. No, not this guy. This guy. This guy is not easy to compute anymore because you've got a product. So I've got to compute this guy. This is very painful to compute the second corrector, let's say, in this extension. Here I've got a product of C1 minus C0 times this guy. This is a bit difficult. But, well, on the theoretical side, it's possible, but then the approach loses its merits, let's say. So, C1 can be any periodic matrix. So, in the same vein, if C1 is not just periodic but stationary, it's the same. At the first order, we can do something. But at the second order, then I've got a product of two guys that are random, and this can behave pretty badly. So you would say that our approach carries over very well to much more general situations up to the first order, and then to be efficient on the second order, we need to assume some more structure. That's yeah, this is very true. Yeah, that's very true. So we stick to discrete because of the first slide. Yeah, I've got this one in there. So that's not what is usually argued. So people are actually interested in fields that takes to value, like a bi-composite, if you wish. And but it's very true. So let me emphasize on what you said. It's very true that the problem which is here to sample people that satisfy this is easier when xi takes continuous value, because I will have actually a situation where I will be able to find those guys and to sample them efficiently, like using dynamics that like the one you shown. Yeah, because I okay.
I'll make a fair comparison of the two Écoles, the 91, for given, say, the number of calls or number of yeah, for given time you have on your computer, what is the best?
Okay, so I forgot to mention that since this guy requires only one PDE to be solved, this guy also. So actually I've got just 2 extra PDEs to solve. So you can compare this as a 2 extra corrector problem at the same price. So actually the increase of price is 2% because we've picked the number of realization to be 100. So for 2% extra cost, let's say that it's 0, right? And so our approach is just the same cost as the plain Monte Carlo approach. So that is why the gain which I've shown is actually very fair. This is really the net cost, the net gain.